Cement and concrete production comes with various environmental challenges. Most prominent is carbon emissions. At present, global cement production yields 2.7 billion tons of CO2 emissions per year. A key question remains: how is it possible to achieve deep carbonization of cement production? Keep watching. Emissions-free cement. One way to reduce cement's carbon footprint is to switch from ordinary Portland cement, OPC, to Portland limestone cement, PLC. The addition of 10% milled limestone in PLC reduces emissions by a tenth. However, with carbon neutrality the goal by 2050, new technologies are a must. New processes are now proposed to limit or entirely bypass traditional calcination. One is electrochemical synthesis. The use of an alkali-activated binder is another. Electrochemical synthesis. Researchers at MIT developed an electrochemical decarbonization reactor that converts calcium carbonate to calcium hydroxide for cement synthesis. The reaction generates hydrogen at the cathode. It generates oxygen and carbon dioxide at the anode. The reaction generates a stream of hydrogen and another stream of oxygen and carbon dioxide. It is possible to harness these gas streams in productive ways. Hydrogen generates power via fuel cells. Oxygen generates power via combustors. And carbon dioxide is readily separated and sequestered. The O2-CO2 gas stream created by the electrochemical process described can serve as an oxy-fuel in a high-temperature kiln. In one experiment, 30 to 35% oxygen-enriched increased kiln production 25 to 50%. Finally, carbon capture becomes more efficient since the flue gas contains a higher concentration of CO2. The hydrogen can also be used to heat cement kilns. In this scenario, renewable energy powers the process. It is already possible to remove CO2 from kiln exhaust through calcium looping, amine scrubbing, and membrane filtration. However, the electrochemical process offers two key advantages. First, it offers the prospect of oxy-fuel combustion. Second, it offers enhanced post-combustion capture of CO2. Compared to regular air combustion, oxy-combustion improves fuel efficiency. The reason is evident. There is no need to heat the 78% of the air that is nitrogen. The absence of nitrogen increases flame temperatures while eliminating nitrous oxide emissions. Alkali-activated binder. Researchers at Johannes Gutenberg University in Mainz, Germany, propose another calcination alternative. They propose the use of an alkaline-activated binder. Their process bypasses calcination by grinding raw lime together with sodium silicate. This eliminates the traditional step of converting raw lime into burnt lime in coal-fired kilns. Instead, it is simply milled with sodium silicate. Milling yields an activated mix of cement components. This mix reacts with the sodium hydroxide solution to yield a calcium silicate hydrate kind of product. The milling of raw lime and sodium silicate occurs at room temperature. Power requirements are just 120 kilowatt-hour/ton, only 1/10 of the energy required for calcination. Widespread adoption of this new process could substantially reduce cement CO2 emissions. The researchers estimate that addressing all the technical challenges could take years. This makes the alkali-activated binder more of a long-term solution. Still, its potential impact on the cement industry's CO2 emissions could be significant, particularly if technological breakthroughs follow. Conclusion. Can an electrochemical process or an alkaline-activated binder prove to be a viable alternative to traditional calcination? Yes, if the process is cost competitive and feasible at scale. Developing the infrastructure to massively deploy such calcination alternatives will take time. With carbon neutrality the long-term goal, the cement industry should consider any new technologies that materially reduce emissions. The Pennsylvania Aggregates and Concrete Association, PACA, reports on developments throughout the industry. We welcome any questions you may have about your upcoming concrete project. Please contact us for further assistance. And if you enjoyed this video, be sure to like, comment, and subscribe.